Hello everyone, in this video we're going to cover the content of the quantum mechanics module. We'll start by discussing the Schrödinger equation. So let's discuss a common problem in quantum mechanics. We're often looking for the particle's wave function, and we get it by solving the Schrödinger equation where h bar is Planck's constant. Given suitable initial conditions, normally psi of x naught 0, the Schrödinger equation determines psi of xt for all future time. But what does the wave function represent? Born's statistical interpretation says that the modulus squared of the wave function gives the probability of finding the particle at the point x and at the time t. More precisely, the integral from a to b of the modulus of the wave function squared is the probability of finding the particle between a and b at time t. This implies that in general, we cannot know the outcome of a quantum experiment with certainty. However, that is not the case when the wave function collapses. If we were to take two measurements straight after each other, we would get the same result. This is because the wave function collapses upon measurement to a spike at a single point where it was measured. However, the wave function soon spreads out again, according to the Schrödinger equation, so the second measurement must be made quickly. Now, let's discuss normalizable solutions to the Schrödinger equation. The statistical interpretation of the wave function implies that the integral from minus infinity to infinity of the modulus of the wave function squared is equal to 1. Normalizing the wave function is the process of multiplying a solution to the Schrödinger equation by a constant so that this equation holds. Once you have normalized the wave function at time t equals 0, the wave function will remain normalized for any future time. However, there are some non-normalizable solutions which can't represent particles. For example, if the integral is infinite, or the trivial solution psi equals 0. Now, let's discuss the expectation value of position, velocity, and momentum. In quantum mechanics, the expectation value is the average measurement of an ensemble of identically prepared systems, not the average of repeated measurements on the same system. For a particle in a state psi, the expectation value of position is given by this integral here. Next, the expectation of velocity is the time derivative of the expectation value of position. Also, the expectation of the momentum of a particle is given by these expressions here. Next, let's discuss why position and momentum are the most important observables. All classical dynamical variables can be expressed in terms of position and momentum. Therefore, to calculate the expectation value of any such quantity, we replace p by minus h bar partial derivative with respect to x, and insert the resulting operator between psi star and psi, and then integrate. Now, let's discuss solving the Schrödinger equation when we assume the potential is independent of time. Then, the Schrödinger equation can be solved by separation of variables, so we write psi of x and t is equal to lowercase psi of x times phi of t. Substituting this into the Schrödinger equation and rearranging, we get this expression here. The left-hand side is only a function of t, the right-hand side is only a function of x, so both sides must be equal to a constant, which we call E because it represents the energy. The left-hand side gives this equation here, which can be solved to show that psi of t is equal to e to the minus I e t over h bar. The right-hand side of the equation gives the time-independent Schrödinger equation. Because energy is a real number, we get the following results. First, the modulus of psi is equal to the modulus of lowercase psi. So, if psi is normalized, then lowercase psi is also normalized. Thus, the modulus of lowercase psi squared gives the probability density function for the particle's position. Next, let's give the Schrödinger equation in terms of the Hamiltonian. In one dimension, the time-independent Schrödinger equation can be written as h hat psi equals e psi, where the Hamiltonian h hat is equal to this expression here. Similarly, in three dimensions, the time-independent Schrödinger equation is given by h hat psi equals e psi, for Hamiltonian given by this expression here. Next, let's explain why the probability density function is independent of time. Although the wave function does depend on time, the probability density given by the modulus of the wave function squared does not. More generally, every expectation value is constant in time, so we get this expression here. Next, let's discuss how to represent the general solution to the Schrödinger equation as the linear superposition of solutions. The time-independent Schrödinger equation has an infinite collection of solutions, which we write as psi n, each with associated separation constant En. Also, because our equation is linear, once we find the separable solutions, we can construct the general solution of this form here, where the coefficients are given by this integral here. Now, let's move on to discuss the solution to the Schrödinger equation for an infinite square well, which has potential given by v of x is equal to 0 for x between 0 and a, and infinity otherwise. Outside the well, the probability of finding the particle is 0, so psi of x is equal to 0. Inside the well, the potential is 0, so the time-independent Schrödinger equation becomes this. Thus, the second derivative of psi with respect to x is equal to minus k squared psi, where k is given by this expression here. This has general solution psi x is equal to a sine kx plus b cos kx. Because psi is continuous, we must have that psi of 0 equals 0 and psi of a equals 0 to join the solutions inside and outside the well. Thus, the only way to have non-trivial solutions is for kn equaling n pi over a. Thus, En is equal to n squared pi squared h bar squared over 2ma squared. Since normalization requires that the integral here equals 1, we can take that a is equal to the square root of 2 over a. Thus, the solutions are psi n of x is equal to the square root of 2 over a times sine of n pi a x. These solutions are orthonormal because we have these expressions here. These solutions are complete because any function f of x can be expressed in this form here, where the coefficients are determined by this integral here. So we can write the general solution to the Schrödinger equation as this expression here. Now let's discuss how to solve the Schrödinger equation for a harmonic oscillator, which has potential given by v of x is equal to a half m omega squared x squared. We can rewrite the time-independent Schrödinger equation as this expression here, where p hat is the momentum operator. Now let's introduce the ladder operators a hat plus or minus, where a hat plus is the raising operator and a hat minus is the lowering operator. Thus we get this expression here for a hat minus a hat plus, and we can rewrite this expression as this form here. Since the commutator of position and momentum is I h bar, we can rewrite a hat minus and a hat plus as this expression here in terms of the Hamiltonian, and we get a similar expression for a hat plus a hat minus. This implies the Schrödinger equation becomes this expression here. Hence we get this expression here, so a hat plus psi is a solution with energy E plus h bar omega. And similarly we can show that a hat minus psi is a solution with energy E minus h bar omega. Applying the lowering operator repeatedly, we can reach a non-normalizable state, because otherwise the energy would become negative. So the ground state psi naught must satisfy a hat minus psi naught equaling 0. Using the definition of a hat minus, we therefore get this equation here. This can be rearranged into this expression here, and therefore we get that psi naught of x is equal to a e to the minus m omega over 2 h bar x squared, where a is some constant. Hence we get the normalized form of this expression here. To determine the energy E naught of the ground state, we substitute into the Schrödinger equation and find this equation here. Using the equation that a hat minus psi naught is equal to 0, we find that E naught is equal to a half h bar omega. Applying the raising operator repeatedly, we get that psi n of x is equal to an a hat plus to the n psi naught of x, with en equal to n plus a half h bar omega, where an is the normalization constant. Combining this result for the energy En, corresponding to the stationary state psi n, with the form of the Hamiltonian for the time-independent Schrödinger equation, we get this expression here. So a hat plus a hat minus psi n is equal to n psi n, And similarly, we can show that a hat minus a hat plus is equal to n plus 1 psi n. Now we're going to move on to discuss solving the Schrödinger equation for free particles, which have potential given by v of x is equal to 0 everywhere. We can write the Schrödinger equation as the second derivative of psi with respect to x, equaling minus k squared psi, where k is equal to this expression here. This differs from the infinite square well, because there are no boundary conditions to restrict the values of k. Because of this, we write the general solution as psi of x equals a e to the ikx plus b e to the ikx. Hence, we get this expression for psi of x and t. The first term in this expression represents a wave travelling to the right, and the second represents a wave of the same energy travelling to the left. We can rewrite the general solution involving just a by allowing k to be positive and negative. However, the wave function is not normalizable, so a free particle cannot exist in a stationary state and thus cannot have a definite energy. But the general solution to the time-dependent Schrödinger equation is still a linear combination of separable solutions, and this wave function can be normalized, but it necessarily carries a range of k's, and hence a range of energies and speeds. We call it a wave packet. To determine psi of k to match the initial wave function, we use Fourier analysis. Since psi of x0 is normalized, these integrals will exist, so we get that psi of k is equal to this expression here. Now, we're going to move on to discuss the delta function potential. The Dirac delta is given by this expression here, with the integral from minus infinity to infinity of the Dirac delta being 1. Since we have that f of x times the Dirac delta of x minus a equals f of a times the Dirac delta of x minus a, we get that the integral from minus infinity to infinity of f of x times the Dirac delta of x minus a equals f of a, which we call the sampling property. And we even get that the integral from a minus epsilon to a plus epsilon of f of x times the Dirac delta of x minus a is equal to f of a for all epsilon greater than 0. The delta function potential is given by v of x is equal to minus alpha times the Dirac delta of x, where alpha is some positive constant. The Schrödinger equation is then given by this expression here. This gives bound states for negative energies and scattering states for positive energies. First, we'll consider the bound states, i.e. when energy is negative. For x negative, we have that v of x is equal to 0, so we can write the Schrödinger equation in this form, where k is given by this expression. The general solution is then psi of x is equal to a e to the minus kx plus b e to the kx, but the first term diverges as x tends to minus infinity, so a equals 0, and thus psi of x is equal to b e to the kx for x negative. And similarly, we find that psi of x is equal to f e to the minus kx for x positive. To connect these solutions, we use the boundary conditions for psi, which are that psi is always continuous and the derivative of psi is continuous except at points where the potential is infinite. The first boundary condition implies that psi of x is equal to this expression here. The second boundary condition says to expect the derivative to be discontinuous at x equals 0, and the delta function determines this discontinuity. First, we integrate the Schrödinger equation from minus epsilon to epsilon and take the limit as epsilon tends to 0, and we get this expression here. The first integral is equal to the derivative of psi evaluated at the two endpoints, and the integral on the right hand side will tend to 0 as epsilon tends to 0. Thus, the discontinuity in the derivative at x equals 0 is equal to this expression here. Substituting our potential in, we get that the discontinuity is given by this expression here. And we can also show that the limit from the right hand side of the derivative of psi is equal to minus bk, and the limit from the left hand side of the derivative is equal to bk, so therefore we also get this expression for the discontinuity. Hence, combining these results, we get that psi of naught is equal to b. Thus, k is equal to m alpha over h bar squared, and the allowed energies are given by these expressions here. By normalizing, we find that b is equal to the square root of m alpha over h bar. Thus, the delta function has exactly one bound state of psi of x equaling this expression here, with e equal to minus m alpha squared over 2h bar squared. Now, we'll move on to discussing the scattering states with energy positive for the delta function potential. For x negative, the Schrödinger equation is given by this expression, and the general solution of psi of x is given by this expression for x negative. And similarly for x positive, we get this expression here for psi of x. The continuity of psi of x at x equals 0 thus implies that f plus g is equal to a plus b. We can also find this expression for the derivative of psi approaching from the right and the derivative of psi approaching from the left. So we get this expression here for the discontinuity in the derivative at x equals 0. Since psi of 0 equals a plus b, the boundary condition on the derivative gives this equation here, and we can rearrange it into this form here, where beta is equal to m alpha over h bar squared k. As we have two equations in four unknowns, we must consider the physical setup to solve the system. In a typical scattering experiment, particles are fired in from one direction, let's say from the left. This implies that g equals 0, a is the amplitude of the incident wave, b is the amplitude of the reflective wave, and f is the amplitude of the transmitted wave. We can find these expressions here for b and f in terms of a. Since the probability of finding the particle at a location is given by the modulus of the wave function squared, the relative probability of an incident particle being reflected back is the reflection coefficient r, which is equal to these expressions here. Similarly, the probability a particle will continue through is the transmission coefficient t, which is equal to these expressions here. Because r and t depend on beta, they depend on energy. Now, we're going to move on to discuss quantum mechanics in 3D. First, let's discuss the Schrödinger equation in 3D. The Schrödinger equation in 3D is given by this equation here. The potential energy V and the wave function psi are functions of r equaling xyz and t. The probability of finding the particle in the infinitesimal volume is given by this expression here. The normalization condition becomes this integral here equaling 1, where the integral is taken over all space. If V is independent of time, there will be a complete set of stationary states, where the spatial wave function psi n satisfies the time-independent Schrödinger equation. The general solution to the time-dependent Schrödinger equation is given by this expression here. If the potential admits a continuous range of states, then the sum becomes an integral. The constants Cn are determined by this integral here. Now, let's discuss the Schrödinger equation in spherical coordinates. A central potential is when V is a function only of the distance from the origin, i.e. we can write V of r as V of r where r is equal to the modulus of r. For central potentials, we adopt the spherical coordinates r, theta, phi. To solve the Schrödinger equation, we seek a separable solution of the form given here. We can rearrange the Schrödinger equation so all the r dependence is on one side and all the theta phi dependence is on the other side. Hence, both sides must equal a constant, which we will call L times L plus 1. The dependence of phi on theta and psi can be written as this equation here, and again we seek a separable solution splitting up the theta and phi. Using the standard approach to find separable solutions, we end up with an expression only in terms of theta and an expression only in terms of phi, both equal to a constant, which we call m squared. The phi equation gives that phi of phi is equal to e to the I m phi, where we allow m to be negative. Increasing phi by 2 pi, we return to the same point in space, so we must satisfy the periodic boundary condition. This implies m must be an integer. The theta equation has a solution which is related to the associated Legendre function. Note that L must be a non-negative integer, and if m is greater than L, then PML is equal to 0. So for a given L, there are 2 plus L possible values of m from minus L to L. Now let's discuss normalizing the wave function. The normalization condition is this integral here, but we split it up into these integrals, where d omega is equal to sine theta d theta d phi. It is often convenient to normalize r and y separately. Thus, we want to satisfy this equation here. It turns out that the orthonormal angular wave functions are the spherical harmonics. The angular part of the wave function is the same for all spherically symmetric potentials. The potential v of r only affects the radial part of the wave function. To find r of r, we substitute u of r is equal to r of r to get the radial equation. This is the one-dimensional Schrödinger equation with effective potential given by this expression here. The extra term is the centrifugal term, which pushes the particles away from the origin. Note that the normalization condition becomes this equation here. Now we're going to apply this to the hydrogen atom. In a hydrogen atom, the potential of an electron is given by this expression here, where E0 is a constant. To simplify the radial equation, we let K equal this expression here, ρ equal Kr, and ρ0 equal this expression here. Then the radial equation becomes this equation here. To find the solution to this, we first examine the asymptotic form of the solutions. As ρ tends to infinity, we have that the second derivative of u with respect to ρ is approximately u. This approximation has general solution given by this expression here, but since e to the ρ tends to infinity, as ρ tends to infinity, we must set b equals 0, so we have that u of ρ is approximately a e to the minus ρ for large ρ. As ρ tends to 0, we have that the second derivative of u with respect to ρ is approximately L times L plus 1 over ρ squared u. This approximation has general solution given by this expression here. But since ρ to the minus L diverges as ρ tends to 0, we set d equals 0, so we have that u of ρ is approximately c ρ to the L plus 1 for small ρ. To solve for u of ρ, we introduce v of ρ such that u of ρ is equal to ρ to the L plus 1 e to the minus ρ v of ρ. We use a power series method to find v of ρ. In doing so, we determine ρ0. Thus, the allowed energies are of this form here, and hence k is of this form here, which equals 1 over an, where a is the most likely distance between the nucleus and the electron. Hence, we have that ρ is equal to r over an. Overall, the spatial wave functions are given by this expression here, and v of ρ is a polynomial of degree n minus L minus 1 related to the Laguerre polynomials. For a given n, the possible values of L are L from 0 to n minus 1. For each L, there are 2 plus L possible values of m, so the total degeneracy of the energy level En is equal to n squared. The orthonormalized hydrogen wave functions are given by this expression here. Now, let's move on to discussing angular momentum. First, let's define angular momentum in quantum mechanics. Classically, angular momentum is defined as the cross product of position and momentum. So, in component form, we have these expressions here. The quantum operators are obtained by replacing px with minus h bar times a partial derivative with respect to x, and similarly for py and pz. Next, let's discuss the commutativity of the components of angular momentum. The components of angular momentum don't commute. Instead, we get the fundamental commutation relations for angular momentum. Because they don't commute, we cannot have simultaneous eigenfunctions for a pair of components of angular momentum. Instead, we introduce the total angular momentum, which is given by L hat squared, which is equal to L hat x squared plus L hat y squared plus L hat z squared. We get that L hat squared commutes with each component of angular momentum. Because L hat squared and L hat z commute, we can find simultaneous eigenstates for them, i.e. we can find a function f and scalars lambda mu such that L hat squared f equals lambda f and L hat z f equals mu f. To do this, we introduce the ladder operators L hat plus or minus using the commutation relations between L hat plus or minus and L hat z, and L hat plus or minus and L hat squared. We can show that L hat plus or minus f is an eigenfunction of L hat plus or minus squared with the same eigenvalue lambda. And similarly, we can show that L hat plus or minus f is an eigenfunction of L hat z with the new eigenvalue mu plus or minus h bar. Hence, L hat plus is the raising operator because it raises the eigenvalue of L hat z by h bar. And similarly, L hat minus is the lowering operator. If we keep applying the raising operator, we'll reach a state where the z component exceeds the total angular momentum. So, there is a state ft such that L hat plus ft equals 0. Let h bar L be the eigenvalue of L hat z associated with the maximum angular momentum, i.e. L hat z ft is equal to h bar L ft and L hat squared ft is equal to lambda ft. We can find lambda plus or minus minus plus is equal to this expression here, i.e. L hat squared is equal to this expression here. Thus we get this equation here. This gives the eigenvalue of L hat squared in terms of the maximum eigenvalue of L hat z. Meanwhile, there's also a state corresponding to the minimum angular momentum Fb with L hat minus Fb equal to 0. Let h bar L bar be the eigenvalue of L hat z corresponding to this state. We can find L hat squared Fb is equal to this expression here, so lambda equals h bar squared L hat times L hat minus 1. We can therefore show that L times L plus 1 is equal to L bar times L bar minus 1. Hence, from this we can show that L bar is equal to minus L. So the eigenvalues of L hat z are m h bar, where m goes from minus L to L in n integer steps. Thus L is equal to minus L plus n, and hence L is equal to n over 2, i.e. L is an integer or a half integer, where L and m are given by these ranges here. For a given L, there are two L plus 1 different values of m. It turns out that the eigenfunctions are the spherical harmonics. Now we'll discuss the formalism of quantum mechanics by first defining a Hilbert space. A Hilbert space is the set of all square integrable functions f of x on an interval, such that the integral from a to b of the modulus of f of x squared is finite. This constitutes a vector space. Wave functions live in a Hilbert space. Next, we'll define the inner product. The inner product of two functions f of x and g of x is equal to the integral from a to b of f of x star g of x. If f and g are square integrable, then they must vanish at plus or minus infinity, and their inner product is a finite number. Note that swapping the order is the same as taking the complex conjugate of the inner product. Also, the inner product of f with itself is equal to the integral from a to b of the modulus of f of x squared, and it is real and non-negative, and it is equal to 0 if and only if f of x is equal to 0. Next, let's define being orthonormal. We say that f of x is normalized if its inner product with itself is equal to 1. We say that f and g are orthonormal if their inner product is equal to 0. A set of functions fn are orthonormal if they are normalized and mutually orthogonal. Now, let's define a complete set of functions. A set of functions is complete if any function, in a Hilbert space, can be expressed as a linear combination of the functions. If the set of functions fn of x are orthonormal, the coefficients cn are given by the inner product of fn with f. Next, let's discuss some results for the expectation value of an observable. The expectation value of an observable q of x and p is equal to the inner product of psi with q hat psi. But the outcome of a measurement is real, so the expectation of q is equal to its complex conjugate. Since the complex conjugate of an inner product reverses the order, we must have that the inner product of psi with q hat psi is equal to the inner product of q hat psi with psi for any wave function psi. So, operators representing observables must have the property that the inner product of f with q hat f is equal to the inner product of q hat f with f for all f of x, and we call such operators Hermitian. Now let's define the Hermitian conjugate. The Hermitian conjugate of an operator q hat is the operator q hat dagger such that the inner product of f with q hat g is equal to the inner product of q hat dagger f with g for all f and g. Therefore, a Hermitian operator is equal to its Hermitian conjugate. Now let's move on to discussing determinate states. Determinate states of a observable q are eigenfunctions of q hat, i.e. q hat psi is equal to q psi. A measurement of q on such a state is certain to give the eigenvalue q. As an example, determinate states of the total energy are eigenfunctions of the Hamiltonian, which is the time-independent Schrödinger equation. Next, we want to define a degenerate spectrum. The collection of all eigenvalues of an operator is called its spectrum. If multiple linearly independent eigenfunctions share the same eigenvalue, the spectrum is degenerate. The normalizable eigenfunctions of a Hermitian operator have two important properties. First, their eigenvalues are real. Second, eigenfunctions belonging to distinct eigenvalues are orthogonal. Now, let's discuss the generalized statistical interpretation. When you measure an observable q on a particle in the state psi, you get one of the eigenvalues of the Hermitian operator q hat. If the spectrum is discrete, the probability of getting the eigenvalue qn associated with the normalized eigenfunction fn of x is cn squared, where cn is the inner product of fn with psi. If the spectrum is continuous, with real eigenvalues qz and associated Dirac orthonormalized eigenfunctions fz, the probability of getting a measurement in the range dz is this expression here, where cz is equal to the inner product of fz with psi. Upon measurement, the wave function collapses to the corresponding eigenstate. The eigenfunctions of the observable operator are complete, so the wave functions can be written as a linear combination of them. Then the total probability must be 1, so we have this equation here, which follows from the normalization of the wave function. Similarly, the expectation value of q is equal to this expression here. Every real number y is an eigenvalue of x, and the corresponding Dirac orthonormalized eigenfunction is the Dirac delta of x minus y. The Dirac orthonormalized eigenfunction of the momentum operator is given by this expression here, and the coefficients are given by the Fourier transform of the spatial wave function. So the probability a measurement of momentum is in the range dp is equal to this expression here. Now let's move on to discuss the generalized uncertainty principle. It states that for two observables a and b, we have that the variance squared of a times the variance squared of b is greater than or equal to 1 over 2i times the expectation of the commutator of a hat and b squared. If we choose a hat equals x and b hat is equal to momentum, we get the original Heisenberg uncertainty principle. Now let's move on to discuss the Dirac notation. Dirac split the notation for the inner product into two pieces called the bra alpha and the ket beta. The ket is a function, and the bra is a linear function of vectors. It acts on a ket and returns a complex number, namely the inner product. In a function space, the bra can be thought of as an instruction to integrate. In a finite dimensional vector space, the kets can be expressed as columns and the bras as rows with components with respect to some basis. Then we get this expression for the inner product. Now let's define the projection operator. The projection operator onto the one-dimensional subspace spanned by the ket alpha is equal to the ket alpha with the bra alpha, and it picks out the portion of any other vector that lies along ket alpha. This allows us to define the identity operator. If the set of kets En is a discrete orthonormal basis, then the identity operator is equal to this sum here. And if the ket En is a Dirac orthonormalized basis, then the identity operator is given by this integral here. In Dirac's bracket notation, the expectation of an operator with respect to f is equal to this expression here, but we often just write it as this here. Next, let's discuss functions of operators. The sum of two operators is given by this equation here, and similarly the product of two operators is given by this equation here. From these we can define the function of operators using a power series expansion. Here are some examples of functions of operators. Now let's move on to discuss the relationship between symmetries and conservation laws. First, let's define a symmetry. In quantum mechanics, a system has a symmetry if the Hamiltonian is unchanged by some transformation. We'll start discussing transformations in space by defining the translation operator. The translation operator takes a function and shifts it a distance a. It is defined by this relation where psi dash of x is equal to the translated function. The translation operator can be expressed in terms of the momentum operator by replacing psi of x minus a by its Taylor series. And we find that the translation operator is equal to e to the minus ia over h bar times the momentum operator. Thus, we say that momentum is the generator of translations. We have that the translation operator is a unitary operator. Now, we'll consider how operators transform. The transformed operator is defined using this equation here, i.e. is the operator that gives the same expectation value in the untranslated state psi as does the operator q hat on the translated state psi dash. Now, let's apply this to the translation operator. We can show this equation here, and because this must hold for all psi, we have that q hat dash is equal to the Hermitian conjugate of the translation operator on q hat on the translation operator. For example, p hat dash is equal to p hat, i.e. the momentum operator is unchanged by the translation transformation. Also, we have that x hat dash is equal to x hat plus a. Knowing how the position and momentum operator behave under translation, we know how any operator behaves because we have this equation here. Now, let's discuss translation symmetry. A system is translationally invariant, i.e. it has translational symmetry, if the Hamiltonian is unchanged by the translation transformation. Because the translation operator is unitary, we can multiply both sides of this equation by the translation operator and obtain that the Hamiltonian of the translation operator is equal to the translation operator of the Hamiltonian. So, a system has translational symmetry if the Hamiltonian commutes with the translation operator. In one dimension, translation symmetry thus implies that the potential of x plus a equals the potential of x. If this equality holds for any a, the system has continuous translational symmetry. If the equality is true for a discrete set of a, the system has discrete translational symmetry. The most important consequence of discrete translational symmetry is Bloch's theorem. It says that the stationary states must be of this form here, where u is a periodic function of x, and e to the iqx is a travelling wave with a wavelength 2 pi over q, where h bar q is called the crystal momentum. To consider continuous translational symmetry, we'll consider an infinitesimal translation, where delta is an infinitesimal length. If the Hamiltonian has continuous translational symmetry, then the Hamiltonian commutes with the translation operator of delta. This implies that the Hamiltonian commutes with the momentum operator. Therefore, momentum is conserved, and we thus get that continuous translational symmetry implies that momentum is conserved. As an aside, let's discuss what conservation means for quantum mechanics. There are two equivalent definitions for an observable Q being conserved. The first is that the expectation value is independent of time. The second is that the probability of getting any value is independent of time. Next, let's discuss the parity operator. So first, we'll define the parity operator in one dimension. The operator reflects a function about the origin and is defined by this relation here. The operator is unitary. Operators transform under a spatial inversion by this relation here. The position and momentum operators are odd under parity. Hence, for any operator, we get this equation for its transformation under parity. A system has inversion symmetry if we have this equation here. Because the parity operator is unitary, this implies that the Hamiltonian commutes with the parity operator. Inversion symmetry therefore requires that the potential is an even function of position. So we can find a complete set of simultaneous eigenstates of the Hamiltonian and the parity operator. Denoting such eigenstates by psi n, we can show that the parity operator on psi n is equal to plus or minus psi n, since the eigenvalues of the parity operator are restricted to plus or minus 1. So the eigenstates of a potential that is an even function of position are themselves even or odd functions. By Iron-Vest's theorem, it follows that if the Hamiltonian has inversion symmetry, then we have this equation here. So, if the wave function of a particle in a symmetric potential is even or odd at t equals 0, then it will remain even or odd at any later time t. Now, let's discuss the parity operator in 3 dimensions. It is defined using one of these two equations. Since position and momentum are odd under parity, any other operator transforms using this expression here. Now, let's discuss pseudovectors and pseudoscalars. Pseudovectors are vectors which are even under parity. For example, the angular momentum operator. Pseudoscalars are scalars which are odd under parity. For example, r hat or r hat. Now, let's move on to discussing rotational symmetry. First, we'll discuss rotations about the z-axis. The operator that rotates a function about the z-axis through an angle alpha is expressed in polar coordinates using this equation here. We can show that this operator takes on this exponential form where L hat z is the z component of the angular momentum. So we call the z component of the angular momentum the generator of rotations about the z-axis. To find out how position and momentum transform under rotation, we use the infinitesimal form of the operator. Then we get these equations for how the components of position transform under rotation about the z-axis. We can represent these equations using this matrix equation. For a general alpha, the matrix equation becomes this. Now, let's move on to discuss general rotations in 3D. First, for a rotation about an axis along the unit vector n, we get that the operator can be written in this exponential form. So n dot L hat is the generator of rotations about the vector pointing along direction n. Now, let's define a vector operator. A vector operator is an operator with 3 components that transforms under rotations as v hat dash is equal to d v hat, where d is a 3×3 matrix. Equivalently, a vector operator may be defined as the operator with 3 components such that the commutation relation with each component of angular momentum is given by this expression here, with I, j and k from 1, 2 and 3, and the 1, 2 and 3 representing x, y and z, where the epsilon ijk is the Levi-Civita symbol defined using this expression here. For example, position, momentum and angular momentum are vector operators. On the other hand, let's define a scalar operator. A scalar operator f hat is unchanged by rotation. Now, let's discuss continuous rotational symmetry. The Hamiltonian is rotationally invariant if the potential is a central potential. Then the Hamiltonian commutes with a rotation by any angle about an arbitrary axis. This must hold for an infinitesimal rotation. So the Hamiltonian must commute with angular momentum. Using Ehrenfest's theorem, we can argue that rotational invariance implies that the derivative of angular momentum is 0 for a central potential. This means that angular momentum conservation is a consequence of rotational invariance. Because the Hamiltonian for a central potential commutes with all 3 components of angular momentum, it also commutes with L hat squared. Therefore, the operators of the Hamiltonian, L hat z and L hat squared, form a complete set of compatible observables, i.e. they commute pairwise for a bound state of a central potential. So, the eigenstates of the Hamiltonian can be chosen to be simultaneous eigenstates of L hat squared and L hat z. In particular, we find these equations here. Now, we're going to consider translations in time. We define an operator that propagates the wave function forward in time by this equation here. For a time-independent Hamiltonian, A power series expansion shows that the operator has this exponential form, so the Hamiltonian is the generator of translations in time. Note that the operator is a unitary operator. Now let's discuss the Heisenberg picture. Operators in the Heisenberg picture, or Heisenberg representation, are the time translations. Now let's compare the Schrödinger picture to the Heisenberg picture. Throughout the module, we've been working in the Schrödinger picture, in which wave functions evolve in time according to the Schrödinger equation. In the Schrödinger picture, the operators of position and momentum have no time dependence of their own, and the time dependence of expectation values comes from the time dependence of the wave function. On the other hand, in the Heisenberg picture, the wave function is constant in time, and the operators evolve in time. So we have this expression here for the expectation of Q. We can show that these two pictures are equivalent. Now, let's move on to discussing time translation invariance. If the Hamiltonian is time dependent, we can write the Schrödinger equation in terms of the time translation operator. However, the time translation operator won't take on the usual exponential form. Time translation means that the time evolution is independent of which time interval we are considering. So, if the system starts out in the state alpha at time t1 and evolves for a time period delta, it will end in the same state beta as it would if the system started in state alpha at time t2 and also evolved for a time period delta. However, we can find that the time translation invariance requires that the Hamiltonian at t1 equals the Hamiltonian at t2. And because this must hold for all t1 and t2, this means the Hamiltonian must be time independent. In this case, Ehrenfest's theorem implies that the time derivative of the Hamiltonian equals 0. Therefore, energy conservation is a consequence of time translation invariance. Now, we're going to move on to discuss time-independent perturbation theory. We'll start by discussing non-degenerate perturbation theory. We assume we can solve the Schrödinger equation where psi n superscript 0 are a complete set of orthonormal eigenfunctions. Now we perturb the potential slightly. Then we want to find the new eigenfunctions and eigenvalues for the perturbed system. In general, we can't solve the Schrödinger equation exactly. Perturbation theory provides a procedure to obtain approximate solutions to the perturbed problem by building on the exact known solution in the unperturbed case. To start with, we write the new Hamiltonian as h hat equals h hat naught plus lambda h hat dash, where lambda is a small number and h hat dash is the perturbation. Next, we write psi n and en as a power series in terms of lambda, where en1 is the first order correction to the nth eigenvalue and psi n1 is the first order correction to the nth eigenfunction. Substituting these power series into the Schrödinger equation, we find that the coefficients of lambda give this equation here, and the coefficients of lambda squared give this equation. In particular, let's discuss the first order theory. We can show that the first order correction to the energy is the expectation value of the perturbation in the unperturbed state. To obtain the first order correction to the wave function, we can get this inhomogeneous linear differential equation for psi n1. Because the unperturbed wave functions constitute a complete set, we can write psi n1 as a linear combination of them. And from this, we can show that Cmn is equal to this expression here. And therefore, we get this expression here for psi n1. Next, let's discuss the second order energies, which are given by this expression here. Now, let's move on to discuss degenerate perturbation theory. Suppose psi a0 and psi b0 are two orthonormalized eigenstates with the same energy E0 for the unperturbed problem with Hamiltonian h hat naught. Any linear combination of these states is still an eigenstate of h hat naught with the same eigenvalue E0. Normally, the perturbation h hat dash breaks the degeneracy, i.e., the common unperturbed energy E0 splits into two. These two states come from two linear combinations of psi a0 and psi b0. The good states are defined as the limit of the exact eigenstates as the perturbation is switched off, i.e. lambda tends to 0. But this isn't a useful definition because if we knew the exact eigenstates, we would not need perturbation theory. Let's assume the good unperturbed states are given by alpha psi A naught plus beta psi B naught, and we want to solve the Schrödinger equation with Hamiltonian given by h hat naught plus lambda h hat dash. Substituting power series representations for E and psi in terms of lambda, the coefficient of lambda can show this equation here and this equation here. Letting wij equal this expression here for I and j equaling A and B, we can write these simultaneous equations using this matrix equation. Let W equal the 2x2 matrix in this equation. Then the eigenvalues of W give the first order corrections to the energy, and the corresponding eigenvectors determine the coefficients alpha and beta that determine the good state. Using the matrix equation, we can show this expression. If WAB equals 0, then we obtain the results from non-degenerate perturbation theory. Next, we'll briefly discuss the variational principle. So, let's define the variational principle. If we let EGS be the ground state energy for a system described by Hamiltonian h hat, the variational principle provides an upper bound for EJS. For any normalized wave function psi, we can show that EJS is less than or equal to the expectation of the Hamiltonian. The main drawback with this method is that we never know how close we are to the target. And moreover, this technique only applies to the ground state. And, as always, thank you for watching.